Hopefully, by this point, you've watched the videos on Markov's, Chebyshev's, and Cantelli's inequality. Before we move on, I just want to sort of clarify that these are bounds on probabilities in all three cases. They're not estimates of those probabilities. They're just sort of worst case scenarios. And if we actually know the distributions that we're using, we can usually do much better, so to speak, because all of those were the general case for a random variable without knowing the actual shape of the distribution. So Chebyshev's inequality said that any distribution no more than 1 over k squared of the distribution would be more than k standard deviations above or below k standard deviations below the mean. So for example, here that would be setting k equals 2. That would tell us that at least 75% of observations would be within 2 standard deviations per mean. Well, if I take a standard normal, I know I've done some hypothesis testing that 95% cut off symmetrically for that is minus 1.96 to plus 1.96 standard deviations around the mean of 0. So if I just take 2 standard deviations below and above, I'd in fact get 95.45%, which is larger than the bound that Chebyshev gives of greater than 75%, but it does also underline that using the bound as an estimate of that would not be very good. And similarly, if I extended that to 3 standard deviations above or below the mean, then yes, the Chebyshev bound would get a bit tighter. It would tell me that I would know that less than 1/9, so at least 8/9 would be between. But in fact, if I know the shape of the distribution as a standard normal, I wouldn't just get greater than 8/9, I would have approximately 99.73%. And in fact, if I take the results from Cantelli telling me that the mean and the median can't differ by more than 1 standard deviation, they differ by exactly 0 standard deviations for a standard normal, or indeed any normal. The mean is the median for a normal distribution. Even more important, really, than Chebyshev's inequality is another consequence of it. So let's say we have a sequence of independent, identically distributed variables, x1, x2, up to xn. My only assumption here is that each of them has the same mean, mu, which is finite, and each of them has the same variance, sigma squared, which is finite. So these can be realizations from any distribution as long as the mean and variance are both finite. So if I work out the distribution, the expectation of the sample mean, sum each of these variables and divide by the number in that sum. Then by the properties of expectation, 1 over n, which every term is effectively multiplied by, is a constant. So I can pull it outside the expectation, and then I know that I'm adding the expectation of n variables, each of which has expectation mu. So I would be getting 1 over n of mu plus mu plus mu plus n times over. So I'm getting 1 over n of n mu, which is mu. If I work out the variance of that, this is a little bit more complicated. So we've seen that the expectation doesn't depend on the sample size. What about the variance? Well, the variance of a constant times a variable is the constant squared times the variance of that variable. So when I pull the 1 over n term outside the variance, it's squared. So I've got 1 over n squared times the variance of the sum. But the variance of the sum is just the sum of the variances when they are independent. Because fully, the variance of x1 plus x2 is the variance of x1 plus the variance of x2 plus twice the covariance of x1 and x2. There's no covariance. They're uncorrelated. They're independent. So now all I'm doing is I'm getting n things added together, each of which is sigma squared. But what I get here, of course, is that is sigma squared over n. So larger samples don't give me any difference in terms of the expected value of the sum of the realizations over n, but they do give me a smaller variance because I get sigma squared over n, that if I have a larger sample, I have a smaller variance around that, which is what I would expect, but larger samples are giving me less uncertainty. They're giving me a more stable picture. So this is when we can resort back to Chebyshev's inequality, because I know that here, if my variable now is the sum of these x's over n, and I know the mean of this is mu, then the probability that that variable minus the mean in absolute value is more than k standard deviations above or below the mean. So the standard deviation here is the square root of the variance. The square root of sigma squared over n is sigma over the square root of n. And that has to be less than or equal to 1 on k squared. If I now rewrite this k standard deviations, or k sigma over root n, as epsilon, then what I can get from my statement where I ended the previous slide is that the probability that the sum of the x's over n minus mu in absolute value, the chance that that exceeds epsilon has to be less than or equal to sigma squared over n epsilon squared. Now, if I've got a larger number of variables, as the number of variables n tends to infinity, then what I can see is that the term on the right, sigma squared over n epsilon squared, sigma squared is a constant. Epsilon, I can just keep constant. But as n tends towards infinity, that term sigma squared over n epsilon squared will tend to 0. So what this does tell me is it doesn't matter how small epsilon is, the probability that my sample mean, the sum of my x's over n, differs from the population mean of mu by more than epsilon, that will tend to 0 as n tends to infinity. So in other words, as the sample size gets extremely large, the population that the average of the variables differs from the true population mean of mu by more than epsilon, whatever any epsilon goes to 0. That I basically become increasingly certain that my sample mean is population mean. This is the weak law of large numbers. And what it says is that as my sample size n gets larger and larger, well, in the infinite limit, then my sample mean, add up all of the x's, divide by n, then the chance it differs from the population mean mu by more than any margin tends to 0. So in other words, I will get a sample mean equal to my population mean with probability 1, assuming that I've got finite expectation and finite variance. Now that's obviously only true in the infinite limit, but it does mean that large samples are effectively guaranteed eventually to converge to the true population mean. So the long run average of any sequence of random variables, assuming finite expectation and variance, will converge to the expected values of those variables with probability 1 certain time.